every single sophisticated thing you do online. I mean, executing a huge stock trade or just logging into the Tarleton portal to check your grades, even hitting purchase on an app. It all comes down to this one, invisible thing, a super fast, totally reliable chat with a database.
Yeah, exactly. And if that conversation fails, or if the data itself is messed up, inconsistent,
Everything stops.
the digital world just grinds to a halt. It's not just slow, it stops. And the costs,
Yeah,
they're astronomical. Trust evaporates.
absolutely. It's all built on organized, structured, and frankly, aggressively protected data. Welcome to the deep dive. Today, we're jumping right into the core of data mastery.
Yeah, our mission today is a really thorough look at the architecture, the governance, the security models that, make reliable organizations tick.
We're hitting those core principles from
Right.
courses like BCIS 4301.
Right, the critical roles, how we guarantee resilience, those next-gen security frameworks. It's stuff you need to know, whether you're going into business, finance, IT, whatever. It's foundational now.
We got a whole stack of sources here, everything from the academic texts that define how transactions work, right up to the latest government guidance on zero trust security.
So that this isn't just theory.
No way. It's about giving you that functional knowledge, the kind that makes you valuable in, any modern company. The kind of knowledge they value at the Dr. Sam Pack College of Business.
Learning to design these systems, manage them, secure them, it's the new baseline competency for business. Honestly, these roles pay well because the knowledge separates the users from the managers, the people who run the backbone of the digital economy.
So if you're ready to become one of those data guardians, stick with us. If you appreciate getting straight to the critical insights, make sure you follow the show.
And check the description. We'll link resources tied to the learning outcomes.
Definitely. Okay, let's get into it. All right, first up, this fundamental split you see in organizations that handle data seriously. The difference between the data administrator, the DA, and the database administrator, the DBA.
Yeah, it's crucial because organizations need accurate, consistent data, right? But our sources are clear. It's too complex for one person. You need these two distinct roles. They have to collaborate, but sometimes they conflict.
That makes sense. The scope is just too big.
It really is. And the stakes are high. Studies keep showing poor data quality is the #1 headache for maybe 64% of organizations.
Wow, nearly 2/3.
Yeah. And if the main system crashes, the cost is insane. We're talking hundreds of thousands of dollars per hour.
Okay, so that pressure necessitates this split focus. Let's break down the DA first, the data administrator. You said if the DBA is the mechanic.
The DA is the architect, the city planner. They're operating way up high, thinking enterprise-wide.
So big picture stuff.
Exactly. The DA is the architect of strategy and meaning. Their focus is the logical level. They're answering the business questions. What data do we actually need? Why do we need it? And crucially, what are the business rules that govern it?
So less about the tech, more about the business rules and the strategy behind the data. Governance.
Precisely. Defining data models, the actual blueprint for all the information. Setting naming conventions so everyone calls the same thing. Well, the same thing. Establishing data quality goals for the whole company. Defining metadata, we'll get more into that later, it's super important. And a big one, compliance. Making sure the company follows the rules, like GDPR for privacy or SOX for financial reporting.
So the DA really separates the what and why of the data from the how it's stored. Like the DA would say, a customer ID must be unique, 10 digits, system generated, and maybe flag how sensitive it is.
Exactly. They own the concept of the data, linking it back to what the business is trying to achieve. Okay, so now let's pivot. The DBA, the database administrator.
Oh, right, if the DA is the architect.
The DBA is the engineer of implementation and performance. They live at the physical level. They worry about keeping the system running smoothly day in, day out.
This is where those deep technical skills, the kind you learn about in SO3, really come in. The sources mentioned the salary reflects this too, right? Like over $117,000 median back in May 2023.
Yeah, it's a high-value skill set. Their world is system health, speed, reliability. So installing and configuring the actual database software, the DBMS, managing who gets access, user accounts, privileges. That's day-to-day security.
Right.
Constantly monitoring performance, watching capacity. And a huge part is query tuning.
Why is this report suddenly taking 5 minutes instead of 5 seconds? Problem.
That's the one. It often means digging into the SQL, making sure the right indexes are there. The DBA figures out how the data is physically stored, how it's accessed efficiently, and critically, how it's protected. backups, recovery plans. That's the DBA's domain. They own the system.
Okay, so here's where I see the potential friction. The DA has the grand vision, the perfect logical standard.
Right.
But the DBA has to make it work with, reality, budgets, server limits, speed demands.
That's exactly the core tension. The friction happens when the DA's logical dream, what the business wants, runs up against the DBA's physical constraints, what the servers can actually do without melting.
Right.
Like, the DA says, we need this new field indexed for instant reports. But the DBA knows indexing everything kills the speed of data entry because it uses up so many resources.
So they have to negotiate. Balance read speed versus write speed.
Constantly. It's a negotiation. The DA sets the policy, the DBA figures out the technical way to enforce it, and they have to work together to balance compliance, performance, and cost. It's a critical collaboration, fulfilling W01, communicating these technical needs and constraints clearly.
And this is changing too, right, with big data, AI.
Oh, absolutely. The DBA role is exploding beyond just, standard relational databases. Now they're managing unstructured data, complex cloud setups like data lakes, data warehouses.
Wow.
And they need to understand these big enterprise-wide security frameworks like the NIST RMF or Zero Trust, which we'll talk about. It demands a whole new level of architectural understanding. Knowing this DA versus DBA split, it's fundamental KO1 stuff for anyone heading into the business world from Tarleton or anywhere else.
Okay, so that collaboration, DA and DBA working together, it's really all aimed at one thing, isn't it? Making sure the business can actually trust the data.
Absolutely. Because if you don't trust the data, what's the point? All the strategy, all the tech, useless. So yeah, let's talk data quality.
What does that mean, practically?
Practically, it means the data is fit for use. Does it meet the needs of the person using it? That's the measure. Low-quality data, it's like poison in the system. People stop trusting the analytics. They make bad decisions, maybe fail compliance audits. It's bad news.
The sources give us this really useful framework. The 6 core dimensions of data quality. It feels like a diagnostic tool, almost.
It is. It gives you the language to pinpoint exactly where the problem lies. Let's walk through them because the differences matter. First, accuracy.
Okay, accuracy. Like, is the address correct?
Exactly. Does the data correctly represent the real world? Is the inventory count in the system the actual count on the shelf? Often, you need to check it against some authoritative source, like the Postal Service database for an address. And an address might look valid, but still be inaccurate, wrong house number, say.
Got it. Number 2.
Completeness. Is the data sufficient? Are required fields actually filled in? Maybe the system lets you save a customer record without an email.
But marketing needs that email.
Right. So for marketing's purpose, that record is incomplete, even if the system allowed it. It's about fitness for a specific use.
Okay.
Third, consistency. This is about matching. Does the same piece of data look the same everywhere? Like, is the phone number formatted as 555-123-4567 in the CRM, but 555-123-4567 in billing? That's a formatting inconsistency, annoying, but fixable. But if the actual data is different, like your account balance shows $100 in one system and $150 in another, that's a deep consistency failure. Needs immediate fixing.
Yikes. Okay, 4th dimension.
Validity. Does the data follow the rules? The defined business rules and formats. It's like a gatekeeper.
So data types, ranges?
Yeah. Does the ZIP code have the right characters? Is the date in the YYYMMDD format? But also business rules like, if a booking date must be in the future, does the system prevent you entering today's date? If not, the data might be saved, but it's invalid for that business process.
Makes sense. 5th.
Uniqueness. Pretty straightforward. No duplicates, no overlaps. Super critical for things like customer profiling. If you have 2 records for the same John Smith, well...
Your marketing is off, your costs are wrong, customer service is confused.
Exactly. Data cleansing projects often spend a lot of time just trying to ensure uniqueness.
All right, and the last one, number 6.
Integrity. This is a bit deeper. It's about maintaining the relationships between data across different tables or even systems. The classic example is referential integrity.
Like foreign keys.
Precisely. Ensuring you can't have an order detail record, a child, if the main order record, the parent, gets deleted. Integrity failures create orphan records, data that points to nothing, basically making it meaningless.
And these problems aren't isolated, are they? They snowball.
They absolutely compound. Invalid date format. Okay, now it's inconsistent when you try to merge it. Fixing it later. Way more expensive and error-prone than getting it right up front.
Which leads us, I guess, to how we document and understand all this. Metadata.
Exactly. Metadata. The classic definition is data about data, but honestly, that undersells it. Its function is way more critical.
So if the data is John Smith, 123 Main Saint, the metadata is?
It describes the what and how. For 123 Main Saint, the metadata might say, data type, variable length string, max length, 255 characters, format, postal standard, source, web order form, last updated, yesterday, data owner, the DA. See?
Okay, yeah, that's detailed. Why is that level of detail so powerful? You said it makes data self-describing.
It empowers the user. Think about it. Without good metadata, every analyst, every manager looking at a report has to stop and guess. What does this column mean? How is it calculated? Where did it come from?
Wasted time.
Huge amounts of wasted time. Sources suggest organizations can face costs up to 40% higher just from poorly maintained metadata. Because people are constantly reinterpreting stuff that should be crystal clear. It's the bridge between the tech side, DBA, and the business side, DA users, critical for WO1 communication.
Okay, and that connects directly to the idea of data standards, right? Metadata defines structure, standards define behavior.
Perfect way to put it. Data standards are the agreed upon rules. Formats, naming conventions, allowed value structures, usually defined by the DA and documented.
Like using the ISO date format everywhere.
Exactly. Or agreeing that all currency is stored in cents, not dollars. The benefit is massive. Standards cut down ambiguity. They make data integration way easier. If everyone follows the rules, you can pull data from sales, inventory, finance, and merge it without needing complex, error-prone cleanup scripts every single time.
So standards basically turn data from isolated bits into a unified, understandable asset for the whole company, a key part of KO1, explaining the role of databases.
Precisely. It's about building that foundation of trust.
Okay, so we've got the roles, the quality focus, the standards. Now let's get into the bedrock of reliability. That promise the database makes when you do something critical, like moving money.
Ah, yes, the guarantee.
You expect it to just work, right? Even if tons of people are using it, even if the power flickers. That guarantee has a name. ACID.
It does. ACID, atomicity, consistency. Fundamental business contract, especially with sensitive stuff, money, medical records, legal agreements. If the system doesn't guarantee ACID, the business is looking at huge liabilities, legal, financial, regulatory. This is core KO3 and KO4 territory, designing schemas and understanding DBMS functions.
Let's define the transaction first. What is that, technically?
Good point. A transaction is just a sequence of database operations that you want to treat as a single logical unit of work.
Like the bank transfer example.
Classic example. Logically, it's one thing. Move money from A to B. But technically, it's at least two steps. Step 1, subtract from account A. Step 2, add to account B. ACID ensures this whole logical unit succeeds or fails cleanly, even under stress.
Okay, let's break down ACID. First, A, atomicity.
Atomicity means all or nothing. The entire sequence, both the debit and the credit, has to complete successfully. If any part fails, maybe the system crashes after the debit but before the credit.
The whole thing gets undone.
Exactly. It's treated as if it never happened, fully rolled back. This prevents those dangerous partial updates. Leaving the database with money deducted but not added, that's chaos. Atomicity ensures you avoid that worst state. The system uses logs to track everything so it can rewind if needed.
Right. Okay, C, consistency.
Consistency ensures the transaction takes the database from one valid state to another valid state. It preserves all the rules you've defined, what we call database invariance.
Invariance. Can you unpack that a bit?
Sure. An invariant is just a rule that must always be true in your data model. In the bank example, maybe a rule is total assets in the ledger must equal the sum of all customer balances. Or maybe an account balance can never be negative.
Okay.
If a transaction tries to do something that breaks one of those rules, like withdrawing more money than is in the account, violating the non-negative balance invariant,
The system stops it.
immediately. The DBMS sees the rule violation and says, nope, cancels the transaction, rolls it back. Consistency is about protecting the integrity of the data model itself. Constraints, triggers, rules, they all have to hold.
All right. The third letter, I. Isolation. That sounds tricky, especially with lots of users at once.
It is where the real complexity lies. Isolation guarantees that even if thousands of transactions are running concurrently, reading and writing data at the same time, they behave as if they ran one after another sequentially.
Without that, you get chaos.
You get what are called concurrency anomalies. Imagine everyone trying to buy the last concert ticket at the exact same second. Without isolation, bad things happen.
Like what are the classic failures?
3 main ones you need to know. First, the dirty read. Transaction 1 reads data that Transaction 2 wrote, but T2 hasn't committed yet. If T2 then rolls back.
T1 made a decision based on data that, never officially existed.
Precisely. Very dangerous. Second, the lost update. 2 transactions read the same value. Both modify it. T1 writes its change. Then T2 writes its change, completely overwriting T1's update without realizing it. T1's work is just gone. Lost.
Ouch. And the third one, you mentioned phantom reads.
Yeah, the phantom read. This one's subtle. Transaction 1 runs a query, maybe counts all open orders, finds 10. While T1 is still running, Transaction 2 inserts a new order that meets T1's criteria. If T1 runs its count query again.
Suddenly there are 11 orders. A phantom appeared.
Exactly. It messes up calculations and logic. Isolation's job is to prevent all these dirty reads, lost updates, phantom reads to keep the process sane. This is key for SO3, applying optimization and security.
So how do databases actually achieve this? How do they keep concurrent transactions separate?
Sophisticated mechanisms. Broadly, you have pessimistic and optimistic approaches. The classic pessimistic one is two-phase locking, 2PL.
Locking?
Yeah. Transactions have to acquire a lock on data before they can read or write it. They hold on to those locks until they're completely finished. It guarantees isolation, but
it can slow things down if everyone's waiting for locks.
Exactly. It can lead to bottlenecks. The optimistic approach tries to avoid that.
Which...
Multi-version concurrency control, MVCC, sometimes called snapshot isolation. Instead of locking when a transaction starts, the database gives it a consistent snapshot, a read-only view of the database as it looked at that exact moment.
So readers don't block writers and writers don't block readers.
Generally, yes. Leads to much higher concurrency, better availability. The trade-off is it needs more storage space to keep track of those different data versions.
Okay, that makes sense. Finally, the D in AC, durability.
The promise of permanence. Durability guarantees that once a transaction is successfully committed, its changes are permanent. They will survive any subsequent system failure, crashes, power outages, whatever.
How does it guarantee that? Isn't there a risk of crashing right after committing but before writing to disk?
There is, which is why we use write-ahead logging, WAL. This is the implementation secret sauce.
Write-ahead logging.
Yeah. Before the database actually writes the change data to the main database files on disk, it first writes a record of the change to a special persistent log file also on disk. That log write happens first.
Ah, ahead of the main write.
Exactly. So if the system crashes after the commit message but before the main data files are updated, it doesn't matter. When the system restarts, it checks the log, sees the committed transaction that didn't make it to the main files, and replays it from the log. Ensures the change is never lost. Durability achieved.
Wow. Okay, so ACID is the gold standard for relational databases, but you mentioned BAAS earlier as a contrast. KO5, exploring alternatives.
Right. ACID versus BAAS. BAAS stands for basically available, soft state, eventually consistent. It's a different philosophy, often used in massive distributed systems like NoSQL databases.
So what's the core trade-off?
It boils down to consistency versus availability. ACID prioritizes consistency. If a rule is broken or there's a conflict, the system will likely fail the transaction to maintain perfect consistency. Availability might suffer momentarily.
Yeah.
BAAS prioritizes availability. The system will likely allow operations even if it means temporary inconsistency. Users can almost always read and write, but the data they see might be slightly stale or conflicting for a short period. The promise is it will become consistent eventually.
So for something like social media feeds or product catalogs where being always available is key and slight temporary inconsistency isn't catastrophic, BAAS might be okay.
Exactly, but for banking, medical records, anything where absolute immediate correctness, consistency is non-negotiable.
Yeah.
You need ACID. It's a fundamental architectural choice with huge business implications.
All right, so ACD guarantees the reliability. Now let's talk about protecting the data itself, the security aspect. We usually start with the CIA triad, right?
Yep, the classic framework. Confidentiality, integrity, availability, it defines the goals. Confidentiality, keeps secret secret. Only authorized people see sensitive data.
Like ensuring payroll clerks can't see executive salaries.
Exactly. Integrity. Prevent unauthorized changes. Data shouldn't be tampered with. Constraints help here, but also access controls.
And availability, making sure authorized users can get to the data when they need it. Preventing downtime, denial of service attacks. This aligns with KO4, evaluating DBMS functions and trade-offs.
But security today is way more complex than just CIA. We face risks to the data, like ransomware, risks from using the data, like algorithmic bias, risks in the data, like it being inaccurate or outdated, and risks from sharing it, like third-party breaches.
It's a lot. And it basically broke the old security model, the castle and moat.
Shattered it. That model assumed if you got past the firewall, you were inside and therefore trusted.
Yeah, once you're over the moat and through the gate, you can wander the castle.
And that's how attackers thrived. Breach the perimeter, then move laterally, find the crown jewels, the sensitive database. That implicit trust was the fatal flaw.
Which led to this huge shift. Zero trust, ZT.
Exactly. Zero trust flips the script entirely. The core principle is assume breach. Assume the network is always hostile. Trust is never granted implicitly.
Wow. So no more inside versus outside?
Nope. It focuses on securing the data itself as the new perimeter. Every single request to access data must be continuously verified. Who are you? What are you trying to access? Why do you need it? Is your device secure? Are you where you should be? Trust has to be earned constantly for every interaction.
Okay, that sounds intense. How do you actually enforce that? You mentioned ICAM.
Right. ICAM, Identity, Credential, and Access Management, is the engine driving ZT. And the absolute bedrock principle within ICAM is the principle of least privilege, PLE.
Least privilege.
Yeah.
Give people only the minimum access they need to do their job.
Exactly that. Nothing more. If you only need to read customer names, you get read-only access, select, to that specific table or view. No ability to change, update, or delete anything. Minimizes the potential damage if an account is compromised. This is SO3 again, applying security strategies.
Makes sense. How do we manage those permissions across, like, thousands of users?
Through access control mechanisms. The most common starting point is role-based access control, RBAC. You define roles, sales rep, accountant, DBA, and assign permissions to the roles, then assign users to roles. It's static, relatively simple.
But Zero Trust wants more dynamic control.
Yes. RBAC is often not granular enough, so we move towards things like ABA and CBAC.
Okay, ABAC, attribute-based access control. How's that different?
ABAC looks at attributes characteristics of the user, like clearance level, department, the resource being accessed, data sensitivity, classification, and even the environment, time of day, location. Policies become more like rules. Allow access, if user role is doctor, and D resource is patient record, and action is read, and patient is assigned to this doctor. Much more fine-grained.
Okay. And CBAC, context-based. This likes this one, right?
Yeah, CISA recommends context-based access control, CBAC, because it adds dynamic context to the ABAC decision. It asks, is the user logging in from a known trusted device? Is the device's security posture healthy, patched, running endpoint protection? Is the login coming from an expected geographic location or network?
So it's constantly evaluating the situation.
Continuously. It combines the static role from RBAC with the attributes from ABAC and adds this real-time context. Access isn't just granted once, it's continuously assessed. If the context changes, maybe the user tries to access data from a risky network, access can be revoked or requires step-up authentication, even mid-session.
That sounds much more robust. Where do things like encryption fit in?
Those are data-centric controls, bringing security right to the data asset itself. Encryption is key, encrypting data at rest when it's stored on disk and in transit when it's moving across the network. Also, things like data loss prevention, DLP tools that scan outgoing traffic for sensitive patterns, data masking to hide parts of sensitive data, even from legitimate users, like showing only the last 4 digits of a credit card, or tokenization to replace sensitive data with non-sensitive tokens.
Can you give a quick example of how ZT uses microsegmentation with databases?
Sure, old way. Attacker gets on a sales laptop inside the company network. From there, maybe they can scan and find the HR database because it's also inside. Zero trust way? We use microsegmentation. We define a policy saying the sales application server is allowed to talk only to the sales database on specific ports for specific types of queries. That compromised sales laptop, it tries to connect to the HR database. The policy enforcement point, a firewall, a proxy, whatever, sees this unexpected traffic flow. It violates the policy. Blocked. The HR database is protected even if they're on the same network segment physically.
So isolation isn't just for transactions, it's for network access, too.
Exactly. And that requires continuous monitoring. You can't just set policies and forget them. You need tools like UEBA, user and entity behavior analytics watching constantly.
And like for weird stuff.
Yeah, anomalies. A user suddenly downloading 100x more data than usual, someone logging in from 2 countries at once, alerts fire. ZT isn't a one-time gate, it's a continuous verification loop.
Okay, so ZT is about proactive defense.
Yeah.
But things still go wrong.
Yeah.
Systems fail. Disasters happen. Ransomware hits.
Yep, reality bites.
So we need the safety net, the DBA's ultimate insurance policy, backup and recovery.
Absolutely non-negotiable. As we said, downtime is cripplingly expensive. Data loss can be fatal for a business. A solid, tested backup and recovery plan. It's arguably the most critical part of the DBA's job, tying back to KO1, KO4, and SO3. If you can't recover the data, nothing else matters.
And building that plan means understanding the different backup types. Let's start with the simplest, the full backup.
Right. A full backup is exactly what it sounds like. A complete copy of the entire database at a specific point in time.
Pros and cons.
Prosam. Simple, recovery is straightforward. You just restore that one backup set. Con, slow, takes the longest time to run, uses the most storage, puts the biggest load on the system while it's running. Big places might do these weekly, maybe nightly if they can swing it.
So because fulls are heavy, we need other options for more frequent backups in between, like incremental and differential.
Exactly. Let's take incremental backup first. This copies only the data that has changed since the last backup, whatever type that was full or another incremental.
So very small, very fast backups.
Super fast to run, minimal storage needed, great for capturing changes frequently.
But it's always a but. Recovery.
Recovery is the downside. It's complex, sequential. Let's say you do a full backup Sunday night, then incrementals every night. If the database crashes Friday afternoon, you need Sunday's full backup.
Okay.
PLUS Mondays incremental, PLUS Tuesdays, PLUS Wednesdays, PLUS Thursdays. You need the whole chain. If any one of those incrementals is bad or missing,
You can't get back to Friday afternoon.
you're stuck. The whole chain breaks. That dependency is risky.
Which makes the other option, differential backup, look pretty good sometimes.
It can be. A differential backup copies all the data that has changed since the last full backup.
Okay, how does that work? Week long. Full on Sunday.
Monday's differential copies all changes since Sunday. Tuesday's differential copies all changes since Sunday. So Mondays plus Tuesdays. Wednesday's copies all changes since Sunday. Monday plus Tuesday plus Wednesday.
Ah, so the differential files get bigger each day.
They do. They grow throughout the week, using more storage than incrementals. But the payoff comes during recovery.
Simpler recovery.
Much simpler. To restore to Friday afternoon, you only need 2 things. Sunday's full backup and Thursday's differential backup, the latest one. That's it.
Way fewer moving parts, less chance of failure, faster restore time.
Exactly. It significantly reduces the recovery time objective, the RTO. The trade-off is, yeah, they take a bit longer to run than incrementals and use more storage as the week goes on. Choosing between incremental and differential is a direct calculation of risk versus resource cost.
And that choice is driven by those business metrics you mentioned, RPO and RTO.
Crucial concepts. Recovery point objective, RPO. How much data, measured in time, can the business afford to lose? If the RPO is 1 hour, you must back up at least every hour. If it's 0, you need real-time replication, basically.
Okay, and RTO.
Recovery time objective, RTO. How quickly does the system need to be back online and working after a failure? A short RTO, needing to be back up in minutes, pushes you towards simpler, faster recovery methods like differentials or even expensive high-availability clusters.
So RPO dictates backup frequency, RTO dictates backup method, and recovery complexity.
You got it. They're the business drivers for the whole backup strategy.
And beyond just the type of backup file, there's the physical strategy, that 3-2-1 rule.
Yeah, the 3-2-1 rule. It's like the gold standard mantra for resilience against local disasters or ransomware. Simple but powerful. Keep 3 total copies of your data.
Primary plus 2 backups.
Right. Store those copies on 2 different types of media.
It's like disk and tape,
Yeah.
or disk and cloud storage. Protects against one type of media failing.
Exactly. And the critical part, keep one of those copies off-site, physically separate. Even better if it's air-gapped, meaning logically disconnected from the network most of the time.
So fire, flood, ransomware, encrypting everything connected.
Yeah.
That off-site, maybe air-gapped copy is your last line of defense.
It's your ultimate fallback. Following 3-2-1 ensures that durability promise from ACID actually holds up even when disaster strikes. #outro. Wow, we covered a lot of ground there. From the high-level strategy of the DA down to the nitty-gritty technical work of the DBA, ensuring things run smoothly and securely.
Yeah, we really unpacked those dual roles, the DA setting the what, the DBA managing the how,
Yeah.
and we hit the foundation of trust, those 6 dimensions of data quality, with metadata as that vital communication link, essential KO1 stuff.
And then the core guarantees, ACD. We broke down atomicity, consistency, isolation, mentioning 2PL and MVCC and durability, showing how they form that non-negotiable contract. That's deep into KO3 and KO4.
Plus the huge shift to zero trust security,
Yeah.
thinking of data as the perimeter, enforcing least privilege using dynamic CBAC, and having that 3-2-1 backup plan driven by RPO and RTO as the safety net, covering key parts of SO3.
Whether you end up defining policy, writing SQL, or designing these resilient systems, understanding all these interconnected layers, well, it makes you incredibly valuable. It's the kind of practical knowledge emphasized at the Dr. Sam Pack College of Business.
Absolutely. Well, thanks for joining us on this deep dive. Definitely follow the show if you found this useful, and please check the description for those extra resources mapped to the learning outcomes.
Yeah, do that. And until next time, keep exploring the world behind the data.
But before we sign off, here's something to chew on. Think about how totally dependent we are on these database guarantees. If tomorrow ACD just stopped working everywhere, if atomicity, consistency, isolation, durability just vanished from every major database, how fast would the global economy literally seize up? What's the real hidden cost of losing that fundamental database trust? And what does thinking about that tell you at the power you gain by mastering these systems?